Welcome to Module 5, Number Systems. This is a math module, not a networking concepts module. Binary and hex conversion. Set expectations up front. This feels unfamiliar at first, but gets fast with repetition, and it's the direct foundation for subnetting later in the course. Worth extra time on the tip slides throughout. Objective: convert numbers between decimal, binary, and hexadecimal. Two topics, shown on screen: binary number system and hexadecimal number system. Reassure students with the note on screen. It's genuinely not that hard once a few tricks click, and this deck is built around exactly those tricks. IPv4 addresses are natively binary, just ones and zeros, bits, because that's what devices actually use to identify each other. Humans convert them to decimal because it's easier to read. Each address is 32 bits total, split into 4 8-bit octets, shown in the binary to decimal translation graphic. Positional notation means a digit's value depends on where it sits, exactly how decimal already works. In 1234, the columns are 1000s, 100s, 10s, 1s. Binary works identically, but the radix is 2 instead of 10, so each position doubles instead of multiplying by 10. 1 2 8 6 4 3 2 1 6 8 4 2 1 for 1 byte. This is the single most important thing to memorize in this module. 1 2 8 6 4 3 2 1 6 8 4 2 1, doubling each step. Have students say it out loud, then write it from memory a few times right now. Every conversion in this module, and subnetting later in the course, runs through this sequence, so time spent now pays off all semester. To convert binary to decimal, split the address into 4 8-bit octets. Line each octet's bits up under the 1 2 8 6 4 3 2 1 6 8 4 2 1 table. Multiply each bit by its column value, then add up only the columns where the bit is a 1. Repeat for all 4 octets to get the full dotted decimal address. Worked example on screen. Octet 11 million. Only the 128 and 64 columns have a 1. Everything else is 0. So 128 plus 64 equals 192. Every other column contributes nothing since multiplying by 0 zeros it out. Walk this slowly. It's the exact mechanical process students will repeat for the rest of the module. Second big memorization tool. An all-ones octet is always 255. Even more useful, memorize the running total as bits turn on left to right. 128, 192, 224, 240, 248, 252, 254, 255. These 8 numbers will show up constantly once subnetting starts. Recognizing them on site saves major time later. Converting decimal to binary reverses the process. At each column ask, does the remaining number fit here? If yes, place a 1 and subtract that column's value. If no, place a 0 and move on. By the last column, the remainder should hit exactly 0. That's how you confirm the conversion is correct. Simplify the algorithm to one repeated question. Does the biggest number left over fit here? Yes means write 1 and subtract. No means write 0 and move on, no subtraction. That's the entire process, asked 8 times in a row, shown as a simple decision loop on screen. Strip away the formal wording, and this is genuinely all there is to it. Worked example. Octet 1 of 192.168.10.11. Is 192 greater than equals 128? Yes. Write 1, remainder 64. Is 64 greater than equals 64? Yes. Write 1, remainder 0. Every remaining column is 0, since nothing is left over. Result: 192 equals 11 million. Walk each question out loud, so students hear the pattern repeating. Octet 2, the number 168 to 168 greater than equals 128? Yes. Write 1, remainder 40. 40 greater than equals 64? No. Write 0. 40 greater than equals 32? Yes. Write 1, remainder 8. 8 greater than equals 16? No. Write 0. 8 greater than equals 8? Yes. Write 1, remainder 0. Result: 168 equals 10,101,000. This example has more no's than the first, good for showing the full pattern. Octet 3, the number 10, is small enough to skip straight to addition. 10 equals 8 plus 2, so the 8 column and 2 column each get a 1, everything else stays 0. Result: 10 equals 0,000,1010. Point out to students that small numbers like this often don't need the full step-by-step question process. Octet 4, the number 11 to 11 equals 8 plus 2 plus 1, so those 3 columns each get a 1. Result: 11 equals 0,000,1,011. This completes the running example. All 4 octets of 192.168.10.11 have now been converted individually, ready to assemble on the next slide. Put all 4 converted octets together. 192.168.10.11 in decimal is exactly the same address as 11,010,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000,10,000 only ever see the binary version. The decimal version exists purely for human convenience. Biggest shortcut in the whole module. One hex digit always equals exactly 4 bits, no exceptions. Split any byte into a left nibble and right nibble, 4 bits each. Convert each with the small 8421 table. Then map each result to one hex digit, 0 to 9, then A equals 10, through F equals 15. One scary conversion becomes 2 tiny easy ones. Hexadecimal is base 16, using 0 to 9 and AF. It shows up in networking for IPv6 addresses and Ethernet MAC addresses. IPv6 addresses are 128 bits total, written as 8 groups of 4 hex digits called hextets, separated by colons, shown on screen with the full address broken out by color. Worked example, decimal 168 to hex. Convert to 8-bit binary first, 10,101,000. Split into 2 nibbles, 10, 10, and 1000. Convert each nibble separately, 10, 10 equals A, 1000 equals 8. Final answer, 168 equals A8 in hex. This is the nibble shortcut from slide 16, applied to a real conversion. Reverse example, hex D2 to decimal. Convert each hex digit to its 4-bit binary. D equals 1101, 2 equals 0010. Combine into one 8-bit binary number, 11,010,010. Then convert that binary to decimal using the positional table, 210. Final answer, D2 equals 210 in decimal. Close the module by walking each bullet. Binary is how devices represent addresses. Decimal is for humans. Positional notation and 1286432168421 drive every conversion. Binary to decimal adds up the 1 columns. Decimal to binary asks, does it fit? Hex uses 0 to 9, and AF for IPv6/MAC. One hex digit always equals 4 bits. Remind them this gets faster with practice and feeds directly into subnetting.